about neural hierarchical models in ecology, feel free to tweet this talk if you want. My Twitter handle is @mxwlj. So I want to start just with a thought experiment. Suppose we mapped every tree. And it's 2020. This is not really that outlandish of an idea, right? We have high resolution satellite imagery pretty much everywhere, high density LiDAR data in most places. And collectively, we've mapped enough tree stems that we could probably put together a semi-decent training set to train a deep learning classifier to try to find trees across the entire planet. So if we mapped every tree, what would we actually have learned about plant ecology? Well, we know a lot about where plants occurred, but we might not really be able to make inference about plant population dynamics, for example. And the reason should come as no surprise. The data revolution and deep learning on their own simply are not sufficient for scientific inference. And so in statistical ecology, we often use science-based hierarchical models for this purpose. In these models, there's some component that describes how the data arise, some component that describes ecological states and potentially their evolution in space and time, and some component that describes the parameters that we don't know. Occupancy models provide a fairly simple example. Here the states are occupied or not, but the data that we have access to are imperfect. So for example, we might have false absences, where a site is actually occupied by a species, but we failed to detect it. And in this hierarchical model, the parameters are P, the probability of detection, and psi, which is the probability of occupancy. In these models, parameters can depend on covariates, right? So we might have some function f that maps altitude, greenness, temperature, and precipitation to the probability of occupancy. And in many cases, we assume linear relationships between these covariates and the parameters we care about. So for instance, for an occupancy probability, we might use an inverse logit transform and just take a linear combination of our inputs, where beta is a parameter vector that describes the mapping from all of these inputs to our parameter. But we can also accommodate nonlinearity. And there are some great examples in the hierarchical modeling literature of people doing this with a variety of techniques. And I want to think a little bit about whether we can use neural networks for this purpose. Generally speaking, neural networks are just function approximators. So they take some set of inputs, X, map it to a hidden layer or some set of hidden layers, and then output some predicted data, Y hat. So for example, this prediction could be, will I see a duck tomorrow? Or how many ducks can I expect to count tomorrow? But in ecology, our data often are not perfect, right? And predicting data alone is sometimes less satisfying than predicting ecological states and their dynamics. And that's exactly what motivates the development and implementation of hierarchical models to begin with. So if we're not satisfied with simply predicting data with a neural network, what could we do for inference? Neural hierarchical models use neural networks to predict parameters instead of data. All I've done here is I've replaced that Y hat with a parameter that we want to know. In these models, the hierarchical model actually includes a neural network. This is all one model. We can estimate the parameters jointly. And so for all of the models that I'll talk about today, parameter estimation proceeds by minimizing a loss function that can be written like this, where it's an average over n examples, and we're averaging some differentiable log probability. And the nice thing about loss functions like this is they permit stochastic mini-batch optimization, which is just a fancy way to say you never have to load all the data into memory at once, and this allows you to scale to larger data sets. So as a first example, I'll describe a neural joint species dynamic occupancy model. This uses data from the North American Breeding Bird Survey. There's 647 species across 21 years, and in total, the data set consists of around 38 million detection, non-detection observations. In general, dynamic occupancy models track the time evolution of occupancy states. And the processes that we care about are extinction, transitioning from an occupied state to a non-occupied state, and colonization, transitioning from a not occupied state to an occupied state. And here the states are imperfectly observed. All we get are detection data that are subject to false absences. And for this particular neural variant, this is what the architecture looks like. And there are two things that I'll highlight. On the left here is a species encoder. This maps species identities to species-specific weight vectors. And this extends the idea of deep multi-species embedding to share information among species that are in the same genus, family, and order. The second part that I'll highlight is a space-time encoder shown here on the right. And this combines regional, local, and potentially time-varying information into a set of spatiotemporally referenced latent factors, H. And the combination of these factors and these species-specific weights can be used to compute parameter values. So let's zoom in a little bit. And you'll probably see some familiar faces if you're used to working with JSDMs. For example, this is our detection submodel. And you'll notice that there's a dot product here between some latent spatiotemporal factors and some latent species-specific loadings. And we can also include a more traditional linear combination of inputs if we want. So for example, in this model, we have a logit linear effective survey air temperature on the detection probability. On a withheld test set, predictive performance was all right. It was pretty good in the Eastern US where we have a ton of data. The worst performance was observed in the farther north breeding bird survey routes of Alaska, where we don't have quite as much spatial information to borrow. One thing that I want to highlight about this approach is there's no assumption of linear residual dependence among species. And furthermore, there's actually evidence for nonlinear, spatially varying dependence among species. So these plots are showing occupancy probabilities between pairs of species, and each line here is a time series for one breeding bird survey route. Another nice feature of these models is we're estimating parameters that we really care about, right? So like colonization and extinction, and this allows us to make inference about range boundaries. For example, one theoretical expectation is that range boundaries exist because of gradients in colonization and extinction. And for most species, the output from this model is consistent with this theoretical expectation. At the boundaries of species ranges, colonization tended to be low and extinction tended to be high. And from my perspective, one neat thing about this is we're estimating these colonization and extinction parameters while accounting for imperfect detection. As a second example, and this is a little bit more proof of concept and probably doesn't belong in the JSDM session, but I'll do it anyway. Let's think about a convolutional animal movement model. So this is a simulated example. On the left, I'm showing a canopy height model. Yellow is the top of a tree and dark blue is the ground. And I've simulated a movement trajectory for some critter through this landscape. And this critter has two behavioral states, in transit and foraging. Let's suppose that we never observe these states directly, and further that we don't have access to the canopy height model. What if we only have the observed trajectory and aerial imagery? Can we use spatial context to estimate parameters of a movement model? Sure we can. We can parameterize a hidden Markov model using a convolutional neural network. This maps raster input, shown here on the left, these are these image chips, to a transition probability matrix in a more traditional hidden Markov model for animal movement that tracks the time evolution of behavioral states and relates those to observed movement trajectories. And it should come as no surprise that performance for this model is better with no data. So this purple line is showing the performance of this convolutional HMM relative to a naive point extraction model. You wouldn't want to fit this if you had 16 or 32 data points. These are the predictions for the test set. The model is predicting the highest probabilities to transitioning to an in-transit state over bare ground and the highest probability of transitioning to foraging over large trees, consistent with the data generating mechanisms. And what's interesting to me about this is at no point have we actually labeled image chips as containing trees or not. In fact, the movement trajectories themselves act as implicit labels for the model. And one thing I want to reiterate here is that neural hierarchical models augment, they don't replace existing models. So if you have some component of a model that you know, F, you can retain it and approximate some unknown component using a neural network. Right now, I think we're at a really interesting time in statistical ecology and deep learning. There are some really great examples at this conference of people using deep learning in novel ways. I've listed some here. Apologies if I've missed you. But it's worth mentioning that deep learning has a variety of useful function approximators that we can borrow that are designed to work well for tabular data, image data, sequence data, and even network data. And now's a good time for us to be thinking about this, right? Because as ecologists, we're faced with an increasing volume and variety of data. And these function approximators might help us encode and combine this information, blend it together, and learn something about ecology. And this is part of a broader trend towards science-based deep learning. Universal differential equations provide one example. Here, the key idea is that you parameterize a differential equation using a neural network, you retain the dynamics you know, and approximate the dynamics you don't. Another cool example is physics-guided neural networks. Here, the loss function consists of 3 terms: an error term that's a discrepancy between observed and predicted data, a penalty for model complexity, and a penalty for physical inconsistencies. So for instance, how far have you diverged from mass balance? If you want to try these models out, go to this website, click on this link. Thanks, and I'll take any questions.